Imagine, if you will, a crystal. You put the crystal in a loop, expose it to an X-ray beam, and collect the resulting diffraction on a detector. You can then perform this exact process many more times, rotating the crystal a little bit before each exposure. What I outlined for you just now, as most of you probably know, is the basics of crystallography, a technique that's been in use for decades and provided the world with hundreds of thousands of structures of very useful macromolecules such as proteins or nucleic acids. However, what if one crystal is not enough for this? What if your crystals are too small? What if they're too radiation sensitive? What if you would like to do an experiment at ambient temperature, or do something fancy like vary the temperature throughout the experiment, or expose your crystal to an electric current? An alternative procedure involves multiple crystals, each of which is exposed to an X-ray beam or pulse with diffraction collected before the crystal is destroyed. This is the basis of serial crystallography, a technique that really came into its own about a decade ago and has been gaining greater worldwide acceptance with the advent of free electron laser sources. We can summarize it as diffraction data collected from multiple diffracting volumes in a series and then afterwards combined into a single data set. Hi, my name is Artem Lyubimov. I am a staff scientist at the Macromolecular Crystallography Group at the Stanford Synchrotron Radiation Light Source, and this is an overview of serial crystallography at SSRL and LCLS, outlining the techniques, devices, and instruments that we provide to our users. Serial crystallography is a very broad field with many different applications, which can be sort of subdivided into three different subgroups. Injector-based methods typically eject or extrude their sample in a continuous jet from some kind of a nozzle. Drop-on-demand methods rely on an acoustic apparatus to eject a droplet into the air onto a tape and then present it to the X-ray beam. And fixed target methods rely on sample immobilized in either a cryoloop or on a grid or a chip. Each of these is best for particular experimental scenarios, even though there is some overlap between them. Injectors are good for very small crystals and experiments with low background, such as in vacuum. Drop-on-demand methods are typically used for complicated experiments featuring multiple techniques. And fixed target experiments are versatile, especially if you need temperature or humidity control, and the only real reason for why you would choose a loop or a chip or a grid has to do with the size of crystals that are available to you. Most importantly, however, drop-on-demand and injector experiments require large amounts of crystals, whereas fixed target experiments allow you to get away with a limited crystalline sample. I'm going to talk about fixed target experiments today. The data collection strategy for a large crystal in a loop typically involves so-called helical rastering, where the crystal is translated and rotated before each exposure. For chips, there are two main techniques. One is rastering, where data are collected by exposing points on a regularized grid overlaid over your chip or grid. Or targeting, where crystal locations are pinpointed and crystals therefore can be individually targeted. This is the slower of the two approaches, but it yields nearly 100% hit rate. Even though we support all kinds of fixed target devices, allow me to focus on the three most common. The standard cryoloop is good for serial crystallography on large and long crystals. The helical data collection at this stage of development is fully automated. The polymer or silicon microfluidic chips are designed to mobilize crystals in known positions for automated screening or to boost the success of rastering approaches. The laser triggers for caged compounds or other reactions within the crystal can also be used with this system. The multi-crystal holders are compatible with crystal position mapping or with UV crystal detection methods, both of which can be used for automatic screening or data collection. We provide full user support for all of these devices. We will train you in their use. We will guide all of the experiments at our beamlines, and we are always happy to collaborate on the development of any methods or devices you may have in mind. We also offer follow-up services. We can assist you with real-time data evaluation. We can help you process any of the challenging data sets, and we're always happy to help you solve structures from difficult data. Let me talk for a moment about standardized devices. The eagle-eyed amongst you probably noticed that all of the devices I'm showing have a very similar looking magnetic base. This makes them compatible with a standard goniometer that we have installed both at SSRL Beamline 12.1 and at LCLS MFX end station. This goniometer is compatible with nearly every device for conventional or serial techniques, standard or custom, as long as it has this magnetic base that fits the goniometer. At SSRL Beamline 12.1, the goniometer is part of a state-of-the-art data collection system. The X-ray beam has a wide energy range that has been optimized for single wavelength anomalous dispersion methods. It is an intense microbeam with a high flux and a wide range of cross-sections, which enables users to collect data from a variety of diffracting volumes. The instrument has been set up for conventional and serial crystallography involving any device, loop, chip, or jet, and designed for a variety of experiments at cryo or ambient temperatures with full humidity control, as well as compatible with a variety of additional light sources such as UV light triggers that I mentioned before. This setup has been replicated at the LCLS MFX end station. The matching multifunction goniometer configuration, support for fixed target and injector devices, humidity and temperature control environment, and support for additional light sources such as UV makes these sister stations. You can perform the same exact experiment at BL 12.1 and at MFX, with the only difference being whether the radiation is synchrotron or XFEL. At the end station, the fixed target devices can also be used for UV-based crystal detection. In this technique, crystals are illuminated with ultraviolet light, which makes them glow against a dark background. Image analysis can then be used to pinpoint these crystals at specific coordinates. The coordinates can be recorded to a file, which is then transferred to our data collection system that can then individually locate and expose each crystal. Alternatively, users can themselves pre-select crystal positions, save these coordinates in a file, and then send this file to the data collection system and guide data collection this way. Even prior to the global COVID-19 pandemic, SSRL provided for all users remote access to all of our beamlines. We have 4 fully remote accessible beamlines with automated sample mounting, remote sample screening, as well as remote control of experiments at both cryo and ambient temperatures. We also offer automated data processing as well as live data analysis during the experiment itself. The user has full control of the entire experiment. But let me mention the live data analysis for a moment. It is carried out by a program called Interceptor that has been very recently implemented at SSRL. It is based on the popular Dials data processing package developed by the Dials group at the Diamond Light Source in the United Kingdom. ZeroMQ protocol is used to move data from the detector to the software. The images are recorded to files, but otherwise no additional files are recorded, which greatly speeds up the process. Both Dials and Interceptor are open source, with links to all the repositories shown below. Interceptor is a fast and versatile program that provides easy-to-read results and is fully automated, requiring absolutely no user input. It simply persists in the background and processes every image that is collected at the beamline. We have implemented this for several scenarios, but the sky is truly the limit for all the applications of the Interceptor, and efforts to apply it to a variety of different experimental scenarios are ongoing. But we do have it available for both rotation and serial experiments. Results are shown in a chart. On this chart here, you can see in red, the resolution is plotted by every collected frame, and in blue is an image quality score. These are plotted in real time, allowing users to evaluate their results. We can do this at speeds of up to 166 images per second. Users can thus determine if they're getting any diffraction from their crystals, whether if they're doing a single crystal experiment, the crystal is soaking up too much radiation. What the diffraction quality is pretty obvious at a glance, sometimes better than looking at actual diffraction images. And we've already performed several successful experiments using both fixed target and injector-based methods, and Interceptor was instrumental in triaging, evaluating, and improving experiments as they were ongoing. Despite being a relatively novel technique, serial crystallography is now very well established not only at LCLS, that was built for the purpose, but also at SSRL beamlines. We have matching instruments between both LCLS and SSRL facilities and support for a variety of sample delivery devices, especially fixed target devices. And we offer remote access for most, if not all, of these experiments. But really, I've only scratched the surface on this topic. If you would like to know more, have any questions, or even better, would like to use any of these techniques, please contact us at the email addresses shown below. On behalf of the macromolecular crystallography group at SSRL, thank you for watching.